We will be starting today's class with some fundamental problems on mechanics and fluid mechanics. So let us look into problems of this type where let us read this problem, which is actually a challenge problem from a standard book. The question is like that, ki there's a table of height of edge length L. Now the concern is that one leg of the table is slightly shorter than the other three legs, and that small deficit is basically delta H, which is 1 centimeter. The question is, if the shorter leg is touching the ground, the top is slightly tilted, and his concern was to make the top horizontal, you have to put a minimum mass which is diagonally opposite to the shorter leg. If this happens with a minimum mass of m0, the question setter said, find the mass capital M of the tabletop. You have to assume perfectly horizontal floor, uniform tabletop, and very light, thin legs. So what I'm trying to do is, I'm trying to draw the cross-sectional view of the tabletop across the diagonal. So how do we feel the structure to be like? So it's like a tilted tabletop. This is the diagonal of L root 2. On one side, I'm taking the shorter leg. So shorter leg will be just staying on the surface, something of this sort. And the other two legs, one of them is appropriate. And there is one leg which is hidden behind it, which is appropriate. And equal length leg is this. So you can, and this will be in air, right? So if you will take this tabletop and the shorter leg is given to you, so it will bend towards the shorter leg, diagonal counter. That will be of H length, which will be staying on the table. This is also H, right? And if I draw a hypothetical line which is parallel to the surface of the tabletop, this distance seems to be delta H. So this distance basically is H minus delta H. And this distance here is drawn the system through the cross section, diagonal cross section. Now, in this view itself, the weight of the table, like it is acting somewhere here. So it is the center of mass because he is assuming the legs to be very light. So capital Mg is acting here. And he has kept a small mass m0 to balance the tabletop. So basically what will happen is that guy will be kept somewhere here, which is diagonally opposite to this point, where the leg is already like shortened. And that minimum mass which you are keeping here, that is m0. So basically that mass is m0 g. Now remember, as you just put this mass, minimum mass m0 at this place, like this end will just start to lift up. So practically the total torque will just be equal to 0 about this line, or you can say about this edge from this point. And there is a normal reaction which is acting at this point. So like these contact forces are irrelevant for me because we are going to just balance torque about, let's say, this axis or point A. So what I perceive is, and if the edge length of the square tabletop is L, this diagonal was like L root 2. So this is L by root 2 for me, and this is also L by root 2, right? And this is total H now. So this is 90 here. This angle is theta. This angle is theta. Now just balance the talk about this point for the minimum mass. So you can simply say, and similarly, this angle here is also coming out to be theta. Normal to this, normal. So basically, I will say whatever this mg is providing and this m0 g is providing, that should be balanced. So practically mg into this distance, which is h sine theta. I'm just writing the magnitudes from this side. And from the other side, if I write the magnitude, that is clock, and that will be m0 g into the distance. So I'm directly saying this angle here is again theta. So it is L by root 2 the cos theta minus this distance, which is h sine theta. Just check that. Minus h sine theta. So practically we understand like this distance is h sine theta. This is also h sine theta. And that total was L by root 2 cos. Now things seem simple. So if you write this equation, the answer to the question which is required was m. So I should say m is equal to m naught. Now just divide these parameters. It is L by root 2 h cot theta term is there minus h sine by sine 1. So you should be getting this as your answer, where that theta was not given. So let me just write that term here. This is L by root 2. So this distance here is L by root 2. So I should be writing tan theta. In fact, directly I could have written cot. So tan theta is delta H upon L by root 2 term. So just substitute this term cot theta here. That is L by root 2 delta H. So effectively, now if I write my answer, capital M should be equal to m naught into L by H root 2 cot theta term, L by root 2 delta H. So L square, again a root 2 delta H and minus 1. So what you finally get is m naught into L square by 2 H delta H minus 1. So, I mean, presentation of a question is in a given way, but conceptually it is a very straightforward problem. All right, let me take another problem which is based on a similar kind of presentation, a very nice problem based on rotation of a cycle taking a turn where the front and the rear wheels are having some unique orientations. Let us read this problem here. The problem is a boy is driving his bicycle at a constant speed on a circular path on a horizontal ground, and to do so he turns the handle so that the front wheel makes an angle of theta with the line joining the centers of the axles of the wheel. Just look into the orientation carefully. The distance between the axles, that is given to be L to me, yeah, and the coefficient of friction is the same between both the tires and the road. I'll use this point afterwards. The question was, what is the minimum coefficient of friction between the road and the tire so that the cycle does not slip? And there are a few assumptions that the center of mass of the cycle and the boy is equidistant from the axles, and the free fall term is G. Now let me show you the top view of the two tires of this bicycle. So I'll show that orientation. It seems that the front tire, this is the diameter of the tire. So this is a top view. Here I have got the axle, and here I have got the axle of the rear tire, and this is the diameter of that tire. So from top, this is the cycle. And remember, like I'm showing center of mass somewhere here, but in 3D, if you look into it, it will be in a vertical plane where that the center of mass and the two axles are forming a triangle. So from top view, this is the diagram. And he's given that these two distances are, so he has given distance between the axles. So like this distance he has given as L by 2, and this distance is also L by 2. All right, so along the road, the distance has been given. Now, the cycle was moving with the speed of V. Here is the center of mass. I've taken this as my orientation. The dotted line that I've shown here is the orientation of the road along which the cycle is going to take a turn. And the front handle is already rotated by an angle of theta, right? So let me draw the center of curvature, like the normal to this line, right? The velocity is along this normal here, and I find a point about which it is turning. But because the body at this stage cannot be treated as a rigid body completely, because we have axles within the body, so I will be analyzing the center of mass of the body for the force equation. And center of mass is at some distance here. I'm writing that distance as R. Now L by 2, this angle is theta. So I got this angle here. This angle is also theta. This theta is known to me. Now let us look into some forces which are acting on the system to analyze the problem properly. I'm saying from the top view in the cross direction, I can see the weight mg to be acting. In the dot direction, I'll have a normal reaction here, N, and a normal reaction here. Now I'm saying both the normal reactions which are acting, because if you look into the torque balance, if you look into the bicycle like this, I mean, this to be the orientation in the vertical plane, and you are standing on the road and you are watching the bicycle in a transverse way. So to avoid wobbling, like this thing, the torque from the normal reaction from both the sides will be the same. So that's why I've taken normal reaction to be equal as n by 2, n by 2. And top to bottom, I've got only gravity. So I'm convinced that normal reaction at both the locations are equal. Whatever you want to say, equal. You could have called n and you could have said mg by 2. So I'm just writing n by 2 as mg by 2. So this is the first thing. I know that normal reaction is distributed equally in both the times. Now comes the interesting part. If this cycle is not slipping at that juncture of time, that means on the rear wheel, I must have a friction like this, which I'm calling as static friction Fs2, right? And on the front wheel, because I have made that rotation, there's a tendency of going out. So I will have a friction which will act anti to that tendency, and that is Fs1 for me. I don't know the values of Fs1, Fs2, but both are less than the limiting friction because the cycle is not slipping. And as the cycle is taking a turn with a speed of v, so from that frame, if I go into the center of mass, I observe that from that frame, anti to the center of rotation, I'll have a force. So that will be written as mv square upon r. So I'm into the frame of reference of center of mass at that point of time. It is moving in a circular path. So I have shown a force, which is mv square upon r on the center of mass, opposite to the radially inward direction, so radially out. Now, interesting thing is to analyze these forces in this plane, and you can see there is a triangle of forces which is formed. Now, these three black forces will add to be equal to 0. So what I'm saying is Fs1 is acting along this line, mv square upon r is acting along this line, Fs2 is acting along this line. So by concept of Polygon law of vector addition, let me draw a triangle of forces which will make this problem very easy. Fs1 like this, mv square upon r like this, right? And the third guy is vertical. So definitely there will be a triangle which will be similar to this triangle which I have formed here. And this triangle will be having components which is equal to the force magnitudes Fs1, mv square upon r, and Fs2. And because the resultant is 0, they will finally add up to 0. So the head of the final vector is here. And now directly I could have said that if I know the length of these sides here, because you know that this angle is theta, this is L by 2, this is R. So I know this is L cot theta here. And this side here is L by sine theta. I'll keep R as such, this is 90. So let me say that Fs1 is to mv square upon r is to Fs2 should be basically equal to the ratio of lengths of these sides. So it is actually L by sine theta is to r is to L by 2. And now it is a one-line problem, because once you write this, that the resultant of these three vectors are 0 and they are along the sides. So this triangle and this triangle is proportional or similar. Then my only thing that is needed is I want Fs1, Fs2, and I need an inequality. Now remember, even out of Fs1, Fs2, you don't need the both of them, because Fs1 is to Fs2. If you look into Fs1 upon Fs2, that is coming out as L by sine theta upon L by 2. So 2 upon sine theta, it is coming out. So they are in the ratio of 2 by sine theta, and that is less than 1. So Fs1 definitely is greater than Fs2, right? So basically, if you want me to write the limiting minimum coefficient of friction which is required, I knew this thing that Fs1 is a greater, is having a greater value. So if I can ensure that the cycle does not slip at the front end, it is not going to slip at the rear end for a common value of mu. So basically, the answer to the question lies in the equation that I have to ensure that Fs1 should be less than equal to mu into n there, which is mg by 2. And this mu should be the overall limiting mu. So from this equation, whatever mu I get, so if I write mu is greater than equal to 2 Fs1 upon mg, this should be the answer to the question, because this question was, what is the minimum coefficient of friction which is required? So the location where the demand of friction is higher, if you are able to ensure that the cycle does not slip there, it does not slip at the rear end also, you are done with the problem. If you can only write FS1 now. Now this thing is taken care of. This was just to analyze the problem. FS1 is my need. Just look into the ratio. So FS1 upon mv square upon r is L upon sine theta upon r, so into r term here. So basically, I'll have my FS1 as what I'm getting. Let me write. I'll have mv square L upon sine theta multiplied by r square. And what is this r square term here? So by Pythagoras, this is L by 2, this is L cot. So r square is L square by 4 plus L square cot square theta. Now, good thing is all the parameters which are written in this equation are given to you. So my answer is ready now. My answer should be mu is greater than equal to 2 by mg multiplied by fs1. Just substitute this expression mv square L upon sine theta. In bracket, I'll have L square by 4 plus L square cot square theta. That's what I'm getting. So this m is taken care of, and 1 power of L will also go. So L 1 power 1 power. Just arrange this properly and that will be your answer. So it is finally 2v square L upon g sine theta in bracket L by 4 plus L cot square theta. That is the minimum value of mu that we should ensure so that the cycle takes a turn with a constant speed v. So the reason I have taken up this problem is at times, instead of just resolving all the forces, there are a lot of good problems. I mean, where if you observe this thing carefully and use geometry properly, things can ease out beautifully. So that was one thing why I've taken up this problem. Right. So let me take one problem from fluid before I move forward. Now, again, this is beautifully written problem where geometry will ease out this problem like anything. The question was quite straightforward. He said there is a rectangular hole having dimensions a by b. Now, just observe the data carefully. So I have the dimensions of this hole as a by b, that is cut in the horizontal bottom of a large vessel. Close the hole. So somewhere here I have the hole, right? To close the hole, a cuboidal block. So remember, like depth dimension. So in this problem, in the cross direction, everything is b, right? And these edge lengths are c. So like these are c, fine. They are put on it in such a way that the square faces and the diagonal plane remain vertical as shown in the figure. Now a liquid of density rho. Now the interesting thing comes. So if you start pouring liquid here, his only concern is how much mass should my block have so that the hole always remains closed irrespective of the level of liquid in the vessel. So his question is, this cuboidal block, like this vessel, can have infinite dimensions. So I can fill liquid up to whatever height I want, up to infinity, technically speaking. And what he is saying is, give me that mass. So you understand your answer should be something of this sort, like m should be greater than equal to something, minimum. So if I can tell you this value, then whatever you do with the liquid, he's never going to lift, that liquid is never going to lift up the block. That is the question. Now, when you start analyzing the problem, the first thing that comes to me is, initially, when you will fill the liquid up to this height, what is going to happen is, all those forces because of pressure which are going to come, they're going to try to lift up this block, right? So I need to ensure that I have sufficient weight here so that these pressure forces are not able to lift up the block. That is there in my mind. And remember one thing, throughout in this problem, I will never consider P naught. The reason is air pressure is present all over on the upper side. Even in the liquid, everywhere P naught will come. And on the lower side also air is there. So apparently the effect of air, P naught, on the system in its free body diagram at all the possibilities is 0. So forget about P naught. Now start the problem without P naught. So basically, you have got a weight downwards. Now just think of the pressure forces without P naught. So you have got some rho GH kind of terms which are acting up. So I understand that whatever pressure force is coming, I need to have a sufficient weight for that. So I'll keep that much at least. Now let's think further. Now I'm saying if you start pouring more liquid here, there will be some forces, pressure forces, which will have their components down like this. So basically the compensation will come. But why not think about this problem in a different way? Think like this, that with respect to this level, let me use some mean properties. Whatever is this level, let me call the pressure at this level as P, mean. Now I'm saying whenever you will analyze this block, what you are going to do is, if liquid is filled up, like liquid is present, anytime when I write pressure here and take a distance y down and take an equal distance y up, I understand that there will be a rectangular strip here over which pressure will act, and an equivalent strip here, like, and the same thing happens on the left hand side. So I'll take a factor of 2 afterwards. My contention is, if this pressure is P here, the pressure at this level will be P minus rho gy, and the pressure at this level is P plus rho gy. So if this strip area is dA and this strip area is dA, the force which will come downside from here, obviously 45-degree angles will be there, and the force which will come upside here, if you just try to find out the resultant, because horizontal I'm not interested, that will cancel. So basically in the downward direction, you will have P minus rho gy into dA into 1 by root 2 factor, like 1 by root 2 factor. And in the upward direction, you are having P plus rho gy. You understand what I'm trying to do? P is going to cancel. P plus rho gy into dA into 1 by root 2. So effectively, when I take resultant of these forces, this P dA 1 by root 2, P dA 1 by root 2 will cancel. So pressure at this level will apparently cancel from both the points. So now the question changes in terms of zero pressure at this level. The feeling is like this. And you go equal distance up and you go equal distance down. So you understand that practically this term converts into something which is upward. And how much is that? It is like dA by root 2, that term is common. I'll have a rho gy term and I'll have a twice of that, because that is negative. So twice of that. So practically what is happening is, effectively with respect to liquid which is down and up, if I keep on moving up, down equally, so up to what distance can I move? So with respect to this level, I can only go up to this distance. Whatever is this height, I'll write that. If that distance is y naught, let's say, so I can go up to y naught up, and this force will keep on getting added. So you understand that with respect to mean, whatever distance is available downwards, if I just take the same distance upward y naught, I will have a maximum up thrust on my body, which is basically acting upwards and in that situation. And that is the vector sum of these values. I just needed the concept there, because value I can write simply. So as you increase y, your effective vertical force increases. And now what I'm trying to say is, with respect to this y naught, whatever y naught I have got, if I can just write this expression. So if I would have written the integral, I would have written dA by root 2 into rho g into y into 2, this much. And then from the left side, another factor of 2. Then I would have integrated from y is equal to 0 to y is equal to y naught. I'll make a comment finally whether I need to integrate or not. I mean, that is another question. But just as far as the expression is concerned, I'm quite happy with this, that I've got some maximum upthrust up to this position where these positions are symmetric, and if this is equated with my mg, so I am saying this is the mass which this guy is demanding. Because if you keep this much mass, then up to this level, when you will keep on filling liquid, thrust will keep on increasing, maximum pressure, force, whatever it is, and you balance it, so your block is not going to rise. A person can say, what happens if I further add? Because up to this point, my justification is only key. If the level is up to this point, then this block is never going to lift up. Now, the other part of the question I will just give by logic. I don't need a mathematical solution for the next part. What happens if you fill up liquid up to further heights? What else will happen? So let me just explain what else. But before I explain what else, just calculate these values and finish off this problem first. I'll give you justification that why, even if you fill liquid beyond this, up to the top or up to infinity, you don't have to increase the mass further, because this is the limiting value for me. Why I'm saying this is something which you people can think. I'll also explain. I'll give 2 minutes to you. But in that meantime, let us just calculate this value. How much is this coming out to be? So just tell me, first of all, what are you getting as y naught? Now let us do the calculative part of the question. Just calculate this. So I think what he has given is a rectangular. So this distance he has given as a. Yeah. And this will be a by 2 here. These angles are 45. So what is this coming out as? A by 2. And so this is coming out as a by 2, I hope. Check. This is a. This is a by 2. This is a by 2. Like all the angles are 45. 45. So this distance is also coming out as a by 2. If that is the case, then y naught is coming out as the vertical height, and the dimension is c. So vertical height is c by root 2 minus a by 2. Just check that. Is that fine? Width of the hole there is a, so center point a by 2. So this height tan 45, so a by 2. This is a by 2. This is actually c. So the total is c by root 2. I subtracted a by 2. So my y naught in the problem seems to be c by root 2 minus a by 2 as far as the calculation is concerned. And what about dA that you can write here? So as far as the depth is concerned, I've got a dimension of b, right? And just the differential segment that I need to write here. So I know the vertical segment would have been dy, and I'm taking a tilted length. So what I should say, directly I'm saying root 2 dy. If it is fine, root 2 dy. So when you will take cos 45, it will become d. That's fine. So now we are ready with everything. dA, you are going to write b root 2 dy. Rest everything is known to you. Density of liquid is there. Everything is fine. And you have to integrate it from 0 to y naught. And y naught is c minus a by root 2. Just substitute the values, you'll get your answer. So just to summarize the problem here, before the thoughts come, G is getting cancelled. So M limiting, I should say limiting value is coming out as, take out the constants. So rho into 4 by root 2 is coming out, rho 4 by root 2. Why this? B root 2 also came out. Then it became just y dy, y square by 2. So 1 by 2, y naught square, c by root 2 minus a by 2, the whole square. Now let us come to the logic of the problem. So up to this point, we understood that this should be the maximum M. Now my concern is, now let's say if you fill the liquid up to this place. Now I will divide my explanations into 2 segments again. If you fill this system up to this place, beyond this, let me first explain. Now beyond this, if you further fill, what is going to happen? Whatever height you are going to fill up this liquid up to, what I will do, that height will generate an extra pressure of rho gh at this top level. At this top level, for this height, you will generate an extra of rho gh. Now I'm saying, treat that this this layer of liquid is like a layer of air having an excess pressure of rho gh. And by Pascal's law, you understand that rho gh will be transmitted everywhere equally. So definitely on the top, you have extra area available. Here you have lesser area available. So the upward component will be less and downward component will be more. So it is not going to lift up at all. Let me explain again what I'm saying. I am saying if this liquid is filled up to this height, still my explanation for this is left. I will explain. Don't worry. And you can understand now. If this liquid is not filling up to this point, if you fill liquid further from here to here, there will be more forces in the downward direction. So they are not going to lift up the block. Only the weight is going to add up. That force is going to add up in the downward direction. Somebody can say, no, sir. If you fill extra liquid, there will be excess pressure here also. But again, the same concept which I'm making here, whatever height you add up, his direct contribution is here. That is one thing. His contribution in terms of rho g delta h will come here, and not only come here, that contribution goes to all the location. But that equal contribution which goes to all the locations here will have equal area, like y naught equal. So that contribution is going to cancel. So this rho g delta h extra effect at all the locations are going to cancel on their own. And his direct effect here is downward. So my block is not going to lift up. That is first point. Second point, if it does not lift up to here, it does not lift up to here. If it does not lift up to here, now further what happens? If you further fill the liquid, there is no direct contribution in pressure, but indirectly his pressure rho g h, which will come here, will go to all the layers. When it go to all the layers, this area is higher. So his contribution here is more and his contribution here is less. So effective contribution is downward. He is not going to lift up. That's the end of the problem. It's a beautifully written problem, like and at times it's not about writing the solution only. If this would have been a subjective problem, you should have logically concluded that I took this problem step by step. Let me go through the process again. Initially, I started filling liquid here. My weight was downward. I knew that till I fill the liquid up to this point, I will have pressures acting up. So I need to have a weight. Then I thought if I will fill liquid further up, now I was getting confused. There are some forces which are coming down, some are going up. What to do? Then I beautifully used this geometry. I said with respect to the mean level, if I go y up and y down, I took the total of the resultant force. So this much down, this much up, I took the resultant. Result was beautiful. I got the factor to be like this. So I understood that if I keep on moving y down and up simultaneously, this upward force is going to increase till I reach this bottom point, that is y naught. So I took y naught here, y naught here. Now I knew that for all the possible levels of this purple and this color, up to this y naught level, I will have the highest vertical force. I calculated that force and I equated it with mg. I explained already that why I have not taken P naught, because air pressure everywhere will come and that will cancel out. So I forgot air pressure throughout in the problem. Irrelevant because it is coming from all the sides, within the liquid, outside, up, down, everywhere. I calculated it. I got my answer. Now I said, why this is the correct answer? Because with respect to this y naught, you go up to this place. Think again what I'm saying. If you keep on filling liquid here, there will be direct pressures here, which will have downward component. So that I'm happy with that. I need not increase my mass. But by virtue of that excess liquid layer that you have kept, pressure will increase everywhere. So my logic is, don't look into the increase everywhere. First, look into the increase at the top surface. That increase is rho g delta h. Delta h can have any value in between. So it's not about this value. It can have any value in between. Any y value here. Now I am saying that increase is equally propagated. Because other than that rho g delta h, other than that, whatever weight of liquid was there, that you have already considered in the initial analysis of y naught. So that extra is constant, but that constant extra will have some impact here, right? And it will have some impact here. But I'm saying that impact area is equal. So his net impact is 0. And his direct impact here is downward. So I need not increase my mass. So there was no problem up to this point. And then I said, further above this point, if I increase by 10 meter, 20 meter, 1000 meter, whatever you do now, this complete lump of liquid will generate some pressure at this bottom point here. And that I will say is some P prime, which is rho G into whatever is the height. Here is redundant. That has been considered. So I'm saying if that extra pressure comes here, by Pascal's law, it will go to all the locations. Now, when it goes to all the locations here, this is having an excess area and this area is less. So his impact downward is more and his impact upward is less. So his net impact is downward. So why will I increase my mass then? I only needed my minimum mass. So you increase whatever you want to do. It is not going to lift. My point that I've made is, at times I see people justifying this where logic doesn't come properly. Like somebody says weight is there. So I have given a proper logic why it is cancelling. You should understand this concept of mean pressure and how we are cancelling these pressures. And so then you will get your answer to the problem. Yeah, Samarth, you want to say something?
Sir, what will happen if we fill water up to mean level, sir?
It will have a tendency to lift up. So basically, we need to put an appropriate weight to ensure that it is kept down. We have proved that. Initially, when you will fill the liquid up to this level, there will have some impact forces which are moving upward, which will let this block go up. So that's why I'm putting a minimum mass. I calculated that out of all the possibilities of all the levels, this is the maximum requirement. You fulfill my requirement here. When why not will come. In this situation, the upward direction force is the maximum. So if I satisfy my mass up to that level so that the block does not lift, then the level is why not, it will never lift. That's what I've proved.
Yes, sir.
You'll get an answer. Nice. Okay. Let me take one problem now just to engage you in mechanics and electro both. This is a nice question where a lot of good ideas are used. Seems very simple. Let's read the problem. The problem was like two identical metallic plates, area A each. There is a spring having spring constant K. The lower plate is fixed. So understand the lower plate is fixed, right? Upper plate is connected at the middle. So there is no wobbling as such. It is connected at the middle. So it is not going to wobble. And there is a spring here, spring constant K. Now the question is, the other end of the spring is attached to a fixed support when either of the plates have no charge. The equilibrium distance between them and that situation is D. Now comes the question. Now if you close the switch and there's a voltage V, the question is what maximum voltage you should be applying between the plates so that they would never touch each other. He has given that ignore gravity in comparison to the spring force and electrostatic interactions. So basically, you have to only consider the spring and the electrostatic forces, neglect gravity in this problem. So we understand if we are neglecting gravity in the initial state, the spring will be in the natural length. There is no force on this block or this plate. There is no mg. Now the problem comes, as you close the switch, suddenly this gets charged. Because of those plus minus charges, there will be attraction and this guy gets pulled towards the lower guy. Now, what maximum volt? Now, can you tell me how should we go about solving this problem? And let me tell you a few things which you should not be doing. Generally, I found students solving such kind of problems without thinking about the physics of the problem. I generally hate this approach where a student says, sir, I will go to a general position, I will write forces, I will write acceleration, I will find out velocities. Now that approach is fine, but that should not be done before thought. So my first contention is think. First, tell me the exact physics of the problem, why you are doing what you are doing, then we can write the equations. He says that, let's say I was taking Viva in an Olympiad and you are just appearing in that Viva. I'm not interested in the mathematical solution. That's a simple cakewalk if I understand the physics of the problem. Physics of the problem is beautiful. Maximum voltage so that it doesn't hit. Somebody can say, no, sir, I said this guy will start attracting, he will start moving towards it. I will make the velocity 0 when it will just try to hit this lower plate. Definitely that is not the solution, because thought is somewhere else. The idea in this problem is that if you analyze the top plate, just let me analyze the top plate at a general location. What exactly is happening? So I know that at a general location Y from this place, I have a spring force, which is Ky, perfect. At that place, there is a force of electrostatic attraction, and that is Q square upon 2a epsilon naught, 1 upon 2a epsilon naught into Q square. And Q is a function of distance, because that Q can be written as capacitance into voltage. So voltage and capacitance at that place will be A epsilon naught by D minus Y, because the distance between the plates has reduced. So you can understand the two forces in the problem, the spring one and our electrostatic force, both are having variable values. So I understand that when this block is moving down, it is having a variable acceleration, and that acceleration is 1 upon m times the mass term, and the force term was what? A epsilon naught v square upon twice of d minus y the whole square and minus ky. Now comes the interesting portion of the problem. Both these terms are functions of y, right? And to begin with, if you observe, when you start moving down, this force is increasing. So this guy is increasing and this guy is also increasing, because the distance between them is reducing. So that force is increasing. So electrostatic attraction is increasing and the spring force is also increasing. So now there is a problem. I don't know who is increasing more, who is increasing less. I don't know anything here to begin with, but I knew that this force was initially 0. So this guy would have some value. So he would have attracted. Now, what if you want to understand what is going to happen in this problem, then you should basically think about the graph of the two components of this acceleration. Or somebody can say, sir, I have observed the force graph. So basically a student who observes the force versus y graph, looking into this component and this, his analysis will be the best. What he will do is, he will divide his acceleration into two components. He will say, sir, first I observed this. I observe that at y is equal to 0, my guy here, this guy, was having a value A epsilon naught v square upon twice of m, epsilon v square twice of m d square, right? And as y increased, y was increasing, this value was reducing. So my graph was something like a hyperbolic 1 upon y square type of graph. And my graph tend towards infinity when y is tending towards d. This is the beautiful nature of my first component of acceleration. Something of this sort, right? And somebody says, sir, I took the second component. So this guy said ky upon m. Now ky upon m is a linear graph like this. The straight line. I've just drawn the magnitudes, like this magnitude, that magnitude. So this guy has got a magnitude of ky by m. Now there are three possibilities. The purple line, this graph, ky upon m wala graph, that is below this yellow graph and there is no intersection. If this happens, that means this acceleration is always dominating over this. That means the lower plate will keep on attracting the upper plate. That means you are going to hit the lower plate, nobody can stop you. That means definitely this guy is going to hit it. Not only that, there will be a moment when his acceleration will be huge, like his value is going to tend towards infinity after some time. So obviously we do not want this thing in the problem. He has very categorically said, I don't want them to touch each other. So this is not a possibility, so I'll struck it off. I'm not changing this graph, I'm just bothered about this. Well, relatively I have to draw. Second possibility is my purple line just touches this function at one point tangentially and always stays below it. This is also not possible, because this possibility only says that the attractive force wala acceleration is dominating this guy always, At one point it becomes equal and then again it is dominating. So that means my velocity will keep on increasing. At one point the rate of increase will be 0, but by that moment I would have attained some velocity and then again my velocity will increase. So I'm going to hit. So then lies the answer to the question. Basically, the correct solution, the possibility which he is talking about is possible only if my purple graph cuts my yellow graph at two possible locations, which tells me that in the first patch of the problem, my velocity will increase. I'm talking about this patch here and this counter patch. He is below, so velocity will increase. Then purple will dominate, so velocity will decrease because the negative component will be more up to this point. Now the concern is, if after two impacts at this point, now this is the critical point. This is the critical point for me. Here, at least I have to make my velocity tending to 0. If remember, up to this point, acceleration is like attraction is dominating. So definitely the velocity will increase. Between first and second intersection, the velocity is decreasing. And if worst limiting situation is, if at this intersection also, the guy does not stop, then you understand beyond this, again, the yellow curve will be dominant and he will be attracted towards that guy. So he's not going to stop. So you understand the problem setter, what does he want? He wants me to solve for what condition? First of all, we need to find out where they intersect. Like where is this intersection means they are equal. So basically I will be solving for Ay is equal to 0. I will have two roots. Out of those two roots, the higher value, at the higher value, I will also make, at the higher value, I'll also make velocity 0. And for that situation to be fulfilled, I will have some app voltage, and that appropriate voltage is my answer. So the question, the physics of the question is over now. I'll write the maths. Now you read the question and understand what I have said. What maximum voltage in this way can be applied between the plates so that they would not touch each other? So the answer to the question is, he is talking about that voltage, which you should be giving from the beginning, so that their acceleration curves are such that they intersect twice. And while the second intersection happens, the net acceleration becomes 0. At that very juncture, the velocity also just becomes equal to 0. Then the purpose is solved and your guy is not going to hit the front plate. So I will be solving for that limiting value. Now comes the solution, which is the simplest part of the problem. If somebody has understood these things, then he will say, now, sir, it is simple. I will write my equations. I will overcome solution. So like first equation is this. I'm not changing it. You carry on with this acceleration. Your second equation is velocity. So simply just v dv by dy you can write. And I've treated downward direction as positive. And I've taken the starting point, this point as y is equal to 0. So now pursue the maths. So you will write v dv by dy. You will integrate. So you'll have vy square upon 2 in LHS. In RHS, let me just write the terms properly. It is a epsilon naught v square upon twice of m. I'll have dy upon y minus d the whole square. So basically minus 1 upon y minus d. This term will come, and plus, because I'll put a limit, and that term is y is equal to 0. So minus minus, and 1 upon minus d will come there. And the second term is minus k by m, and I'll have y dy. So that is v. I need to write properly. So like k by m, y dy, y square by 2. Observe this thing carefully. The good thing is like 2, 2, and 2 cancels out as such. And now you have vy square term. Just write it properly. You have vy square term, which is a epsilon naught v square divided by m. And I have what I should say, 1 by d minus y term, minus 1 upon d term, and minus ky square upon m term. This guy is your vy square. Because I have to make it 0, I'm not interested in root and all. I will make this expression 0. And this guy, wait a second. Yeah, this is my acceleration versus y. Now I think what I'm going to do is make it equal to 0, because you need not solve that cubic. Because to solve the problem, you need not do like d minus y square y and solve the cubic. Just solve them simultaneously. Solve for a location where both are 0. And that is that unique location. Both cannot be 0 at any other. Like if I am making both of them to be 0, a student can say you are talking about which possibilities. So am I talking about the first possibility? No, because at the first possibility, velocity can never be 0. So if you make this 0, and if you make the other guy also 0, and you solve for that root where both of them are 0, you are solving for the second solution only. So make it simultaneously, make it 0, both of them, and get me the value of capital V for that. That will be your answer. So when you will solve it simultaneously, it will convert. I mean, it won't be a cubic because that d minus y whole square term. So directly I will eliminate a epsilon naught v square upon 2m into d minus y. I'll write it as k y d minus y. I'll convert it into a quadratic. You understand? You will get your solution simply. So it was a nice conceptual problem which should be analyzed properly for you answer problem.
Sir, can we equate areas, sir?
Yes. I mean, not area. I should say you want to make Vy 0, na?
Yes, sir. It means
I have drawn acceleration versus y graph, na? The problem is that.
Yes, sir.
So what you are saying is you can do that, because ultimately when I have done Vy square, na? So basically I have made area under the graph to be equal to 0 only. Hai na?
Yes,
because
sir.
I am making Vy square term finally to be equal to 0. You can do that. No issues. Ay make it 0, Vy square make it 0. So area should also be made equal to 0, and that value should be made equal to 0, and that common root you will get. And there will be two variables, y and v, voltage and y location. So you'll get y location and substitute in the other one, you'll get the voltage. So that is all. So perfectly fine. That makes, because it is actually the work energy theorem equation. I'm writing VdV by dy is basically work done by the force. So you can look into the area also. That is kinetic energy. Okay, so let me take up now. Again, it is a conceptual problem and not a very tough one, but a nicely written problem, because he has used one insulator. Generally, in these problems, we take all conductors. So just read this problem. There are these two charged thin metallic plates A and B, each of area A, and fixed parallel to each other and earthed, right? He has said that I take another identical plate C made up of a dielectric material. So he is treating this dielectric material to be a strong insulating material, like standard conventions. And that material is placed midway between the two plates. The question was, the plate C is given a net positive charge capital Q, which is uniformly distributed over its volume. Now, when you say that volume, it is like thin sheet. So it is more of an area, less of a volume. Question is, if somebody shifts this insulating plate, dielectric plate, by a small distance x leftward, what is the net electrostatic force which will be acting on C if it is shifted a distance x towards plate A? I'll give 1 minute to all of you to think and answer. A very probable kind of question for JEE and may not be a very tough one. So just to analyze the problem, I'll write something in the initial state also and discuss a few things with you. Why I've taken this question is because I want you to, I need to understand how you think such problems. Like, let me tell you what I'm saying. Let's say in the initial state, a student says, fine, like this is Earth, this guy is also Earth, and on the inner side you have kept an insulator, and this insulating guy is having a total charge capital Q distributed over it. So I said, fine, if this distance is d, this distance is also d. In the initial state, my charges will be 0, 0 on the outer side, and on the inner side, it will be minus q by 2, minus q by 2. How I look into this problem is, I think that he is talking about, like, you go, because these are infinite, you go up to infinity and think of it like a close conducting shell, close conductor. ये बंद हो जाएगा ऊपर से और नीचे से. And you have earthed it. So nothing outside. So on the outer surfaces, we are not going to have any charge. So we understand. On the inner side, if you have kept a sheet, by Gauss law now, this is not conducting. But by Gauss law, on the inner surface of conductor, we will be having opposite of this charge. So this was plus Q. I would have total minus is minus Q for sure. And then I can say I use symmetry. I directly said minus Q by 2 minus Q. Perfect. Now comes the problem. If you shift it by a distance x, you take this guy here. This guy now in the final state is still having plus Q. Now I will say still I'll have 0, 0, that property of conductor. I'll have some minus Q1 here and I'll have some minus Q2 here, where I know this thing that Q1 plus Q2 is still equal to Q. You know that. And secondly, when you write the ratio Q1 is to Q2, I'm just saying that should be in the ratio of their capacitance. So basically, I want to write Q1 into D minus X is equal to Q2 into D plus X. I think these two things are clear to you. You think in different methods, like you use your way of thinking. I don't mind it. From basic also, we can justify that these are the results. Why I'm saying by basic, either I will be dropping my potential from this surface to this, the decrease of potential, that should be made equal. And you will get the same relations. And then somebody can say, I will apply Gauss law. I will go into this volume. I will say the field is 0. I'll write field because of all of them. You do whatever you want inside the conductor, you'll get the same result. If you are clear about this, then the problem was a single line objective question. Here the interest was the net force on the C. So in the final state, I should write my answer is the force on this guy. So I knew that Q1 is more. So this attraction is more, that is less. So force will be leftward. What is that? The charge of this guy into field of those guys. The field is sigma upon 2 epsilon naught. So 2 epsilon naught area also I will take, and then the magnitude of charges. So Q1 minus Q2. So my answer should be leftward Q upon 2a epsilon naught into Q1 minus Q2. I have to write. And I think you understand, like both the values are known to you. So Q will again come out to be the common factor. And in Q1, I will have D plus X upon 2D. And Q2, I'll have D minus X upon 2D. Now, just open up the brackets, you'll get your answer. So I think this is clear to all of you. Any issue with distribution of charge to anyone, or like all of you are clear? I think this is simple. So most of you. Fine. Okay. Let us go to another problem and let's see how you analyze these kind of questions. One problem I'll take from rotation, then I'll come back here. Now in this problem, it was nicely written. He said this was from a challenge question. Like question was, there is a uniform annular disk. This is a uniform. He's talking about this disk, a uniform annular disk, and this is having a outer radius capital R, inner radius small r, right? It is coaxially mounted on a fixed cylinder. So he's talking about this inner cylinder. This is the fixed cylinder he's talking about, right? Now the question is, radius of cylinder is slightly smaller than the inner radius of the disk. So basically there is a gap here between the annular disk and this fixed cylinder. There's some gap. So it can rotate freely there as a pulley and fixed cylinder as an axle. The good thing is, he says, the coefficient of friction between the disk and the cylinder is mu here. At all these contact points, it is mu. And now he's talking about a different thing. He's saying there is a light inextensible rope. He's talking about this rope. Supporting two load, this. And remember, there is friction there also, because then only it is moving together. But he's not talking about the mu value there. He has only given mu value here. So now the question comes. The question is, what is the acceleration of the load, capital M? So practically, if I analyze this problem, what I'll do, I'll try to analyze the annular disk. What is happening on the annular disk? So what are the forces that we perceive on the annular disk? So maybe I'll have some tension here. I'll call it T1. I'll have some tension here. It's T2. You understand that on the blocks like T1, MG, you understand these things like T2, capital MG. We all understand that he will go down with A, he will come up with A. This string will start rotating with A. That is fine. Now come to the main concept. What are the forces which I will apply on that annular disk? So I think you'll have some weight of the annular disk. So in this problem, he has given that no mass was given. If you give mass, still I can solve the problem. It was not given, so he has taken light annular disk. So that term is taken care of. Now the only two forces which are remaining is normal reaction and friction from the inner solid cylinder to the annular disk. And because there is a gap here, that contact will happen at a unique point. I'm saying if I've got a axle which is fixed, and if I've got a cylinder over it, and there is a small gap, then obviously when the system will move, it will have a unique contact point that is the common tangent of these two bodies, somewhat like this. I don't know which contact point, but one contact point. And that contact point should be such that if I apply normal reaction and friction, now I'm making a statement. I'm saying that contact is only possible in the first quadrant. In the first quadrant, somewhere here, that contact can happen. And this guy is going to apply a normal reaction on my rotating body, that is the annular disk. And he is also going to apply a kinetic friction, which is mu into N. These two forces. Why this contact happens here? If this contact is anywhere else, the free body diagram for the annular disk cannot be balanced. You can check that. In the first, if you look into the X balance also here, the X is balanced because these T's are vertical. You understand, if you go your N and mu N, you have components back. If you go into the third quadrant, your N is somewhere here, they cannot be balanced. And the fourth quadrant, if N and mu N can be balanced, then the vertical forces cannot be balanced because everything will be vertical. So looking into all the possibilities that come here, and then you can take some theta here. And this angle will be some theta, that is some 90 minus theta. And by balancing now annular disk, I'll have that N cos will be equal to mu N sine. So you understand that there is a unique location of theta, which is tan inverse of 1 by mu, where the contact will happen. Now the things will be easier because once you understand the location where the contact will happen, now calculation of acceleration of the load, I'm writing few things through balance. Just look into it. I'll balance the torque now. If you look into the torque balance about the center, there will be a mu N, which is having a lever arm of small r, right? I'm taking this radius to be small r. This is capital R that is coming. N is not providing any torque. And T2 and T1. So like T1 is supporting it, capital R, and T2 is having T2 into capital R. So you can check the second equation. And third, you just do a simple force balance in the vertical direction. So you'll have this T1 and T2, which is acting downward, is equal to N sine plus mu N cos acting upwards. That is my third. So these three equations are fine. And as far as T1, T2s are concerned here, we are quite well placed. Like T1 minus small mg, that is small m, small a. And fifth one is capital Mg minus T2 is capital M small. Now just observe the 5 equations which you've got. I think mic of Raghav is open, so you can mute yourself, Raghav. Yeah. Now, if you look into the variables in these 5 equations, what are the variables? Just check. Like T1 was an unknown, T2 was an unknown, normal reaction was unknown, theta was unknown, and acceleration was unknown. These 5 unknowns and these 5 equations. T1, T2, N, theta, and A. So 5 unknowns, 5 equations, you can solve properly, you'll get the result. So that was the essence of that problem.
Sir, how can we balance stock, sir? Because it's rotating now.
But it is light, na? So moment of inertia is 0.
Oh, yes.
Otherwise, still you can solve the problem. If you would have given me mass, na, I would have still written equations with appropriate MACM kind of terms. Because this guy cannot have center of mass acceleration. The force I would have balanced. And for torque, I would have written the I alpha equation. And only in the force equation, I will have an extra term of weight of that annular disk. No problem. So here,
Yes, sir.
so you'll get your answer. Just a moment. Let me show you the next problem. Something. Okay, so let me now take up a problem where there is a dielectric and maybe some concepts of surface tension also. Nice, simple, fundamental problem. Just read this problem carefully. Bottom face of a horizontal dielectric slab, right, is coated with a conducting paint, and the center of the top face, I have got a small mercury drop, which does not wet the plate. Perfect. Thickness of the slab is D and relative permittivity, so dielectric constant is given. The question is, now the switch is closed here and the battery voltage is increased gradually so that the mercury drop spreads on the dielectric slab at a negligible rate. So as you are changing the voltage there, that mercury drop is spreading at a uniform rate, which is negligible. Negligible rate, very slow. The question is, at what battery voltage will the mercury drop cover the whole of the upper face of the dielectric? At what voltage can it cover the complete upper face? Surface tension of mercury is sigma. Initial surface area of the drop is negligible as compared to the surface area of mercury when spread. Interesting. Now I'm saying, let me try to observe this problem at a general situation. So what I'll try to do is, I'll just try to write the solution here. So I'll go to a general state. Let me understand what exactly is happening at a general state. At a general state, this is my lower, because you have said that you have painted the dielectric with a metallic paint. So I have a metal plate here. I have my dielectric here. And maybe at general state T is equal to T, this mercury drop, which is acting like a conductor, would have spread up to some distance. And this is like theta symmetric. So I'm just showing the cross-sectional view. And I've got a battery voltage here, V, which is present. What exactly is happening in this problem? So I will solve this by energy method. This seems very straightforward. By energy method, whatever dW, if this is a general state, whatever dW work is done by battery, either it is going as the change of differential electrostatic potential energy stored in the capacitor, or it is going as a change of differential surface energy stored because of the two layers of mercury which are formed at the top. So that is the energy in surface area, surface energy. Now, how do I perceive these terms? I say that dW here will be some dQ into voltage, and that du here is d of some half CV square, right? And d surface is like dA, like sigma is energy per unit area. And if this guy increases his area by dA, so dA, and then because there are two surfaces, so basically a factor of 2d. dA is the increase of area, but actually that mercury drop is not wetting the surface, so he is forming two areas, so 2d. Now comes this point that I could have written this as, because he is keeping voltage to be nearly constant. He's varying it at a very slow rate. So for that differential step, I could have written this as VDC. Now my life is simple. Like I could have said V square DC in that differential step. This is V square by 2 DC plus 2 sigma dA. And this becomes V square DC by 2 is 2 sigma dA. And then it becomes what? V square into DC by dA is equal to 4 sigma. Now the interesting thing comes, How do I observe that DC by DA here? So my contention is, because like capacitance will only be formed between these two metallic surfaces. Like this is metal, but from the upper side it is open circuited, so no charge can sit here. Nothing is sitting here. So the active capacitance, rest of the dielectric will be redundant. Active capacitance will be only this much, and this area I have treated as A. At that junction, remember in this complete analysis, I'm talking about A as this area, not the complete area of the plate. I'm taking my A as variable area of the mercury drop, which is increasing, and finally it will become equal to the total area of the lower plate. So I'm talking about A. So in that context, C for me is A epsilon naught by D, the dielectric constant of this material field here, which is epsilon R. So I got this point quite beautifully, like DC upon DA came out to be a constant, which is epsilon R, epsilon naught upon D, and substituted here. So now the problem is V square into epsilon R, epsilon naught divided by D, epsilon divided by D, V square into this much should be equal to 4 sigma. And then what was required was V. So I should have root of 4 sigma D upon epsilon R, epsilon naught. That should be your answer. So gradually it will take care of everything. If your voltage is kept like this, it will finally cover it in a gradual interval. So just the point was why I've taken this problem. There's so many problems on dielectric which you must have solved. I just took this problem to recap that concept, that all those problems on dielectric can be treated in terms of energy concepts. Think in terms of energy. And because the process is gradual, the rate of flow of charge is very slow, so nothing is coming out as heat. And there is no kinetic energy involved in the system, no other energy involved in the system. So this equation can be. Now, because I'm talking about energy methods, I just wanted you to think, this is one very standard problem. I put up 3 problems in front of you, and you have to logically answer. You don't need to calculate. Like if I give you 2 inclined surfaces, both are inclined at an angle of theta. And I say, I take a ball, I leave it on the incline at one point. I let it come down by a distance of h, vertical height h. Then I do the experiment again. I take the ball again, and the location which was the final point, I put my ball there, I flick it so that it again attains the same height. Listen to the complete question. Initially, it may seem simple. Now I'm giving you 3 situations. 1, when it is frictionless, the simplest one, class 9th problem. 2nd, when it has got a kinetic friction, sliding friction, maybe a class 11th initial problem. 3rd, when air drag is present. And drag is, when I say drag is present, friction is not there directly, but air drag is present. And drag will have some kV raised to the power n behavior, where n is not given to you, but n is a positive number. So like we understand, as we increase, drag will increase. The question was, this is a multiple objective question which you can make, that in the 3 situations, what is the relation between the time taken by the bodies, like one body coming from top to bottom and the other going on the same incline through the same height from bottom to top, same 2 points. We understand in first case answer is equal to 1 is equal to 2. Forget it. Now, 3rd case is my contention. Actually, I want to analyze 3rd. And how do you think about the 3rd case without your mg sine theta, mu mg cos theta? That is like out of contention. I don't want you to think like that. Can you give me a good approach, thought, through which you can analyze that problem? And obviously, I'm more interested into that thought which can be used in any complicated problem. Why I've taken this problem is, student, whenever such problems come, they start writing mg sine, mu mg cos and all those things which are not required for such quality problems. So what I'll do is I'll just try to explain it in a conceptual manner. The point is, if you have these 2 inclines, we are talking about like let it carry on, let it carry on, let it carry on. So I'm talking about this level, the common final level, the common initial level, fine. So these are my common initial points. These are my common final points. I have a common angle theta here. One guy is coming from top to bottom, one guy is bottom to top, and drag is acting. So only let me analyze the drag case. Drag is acting. So how do I analyze the problem is, what I will do, I will take two symmetric patches. I'll take patch. So patch of road here, the symmetric patch. In one case, my ball will be going down from this patch, and another case, my ball is going up. I don't know the velocity of my ball. But let me say, if the guy who is coming down is having some velocity here, V prime, and the guy who's going up in the symmetric patch, these are symmetric patches, symmetric patch, will have some velocity V double prime. Now I'm making a statement. My statement is, the ball which is coming from top to bottom will have lesser speed in all the symmetric patches. So he will take more time. So answer is done. Time of descent will be more than time of ascent. If you can understand this point, if I can explain this, for every patch this happens, then by logic, you're covering a distance in patches, and this guy is going up in patches. In every symmetric patch, my left side guy is having less velocity, and this guy is more. So in every patch, so the time that he will take to cover this patch, because the velocity is less, he will take more time here, he will take less time. In this symmetric patch, more time, less time, more time, less time. So in every patch, if he's taking more, he's taking less. So net is also the same. So the answer now boils down to this point. Can I explain this only? And this is simple energy concept. You are starting from this point, coming down. Maybe you had some potential energy, let's say 100 joule. So out of this potential, something will come into kinetic, and something is lost as drag from here to here. I don't know what is lost, but something is lost. So if the potential here with respect to this point is 100, and this potential is 0, just taken some value. This is valid here also, 0 and 100. Potential energy difference. Now this guy will have a kinetic energy, K prime, which is definitely less than 100. Because 100 में से उसने kinetic energy भी लिया और कुछ losses भी हुए. But when I go from bottom to top, I will have a kinetic energy which is definitely greater than 100. Because out of this kinetic, I have to increase my potential by 100, and I have to overcome the drag also from here to here, which are some losses. So my energy is greater than 100, and this guy's energy less than 100, and half mv square mass is same. So basically, velocity v prime is, because this is less than 100, you understand that his kinetic energy will be less, so speed will be also less, so he will take more time to descend, less 10%. So like without any calculation, logically I can explain the question. And because if I will be setting this problem for JEE Advanced, I won't be asking that thing. And to confuse you, I can give you a hell lot of complicated question. I will say that the drag is minus k v raised to the power 7 by 2 plus v raised to root and whatnot. And everybody will start integrating. And that is where I will judge how All India Rank 1 thinks. So the solution will come through calculus also, but you will take 15 minutes to solve. And the thinker, the topper, will write it in 10 seconds and he will go on. In physics, always in JEE Advanced, you will find this thing that until and unless you come out of maths, you can never be a top 10 ranker. Remember my point. By hard work, by maths, you can go up to top 100. But final 5 students, 7 students, 10 students, you have to have a physics bent of brain. Maths is our utility tool, but physics is not only maths. So many questions of this type can be solved, but just take care of that. And now I leave it, because I have less time. I leave it for you to think, like if kinetic friction was present and you are looking into mu mg cos theta, maybe you can say that I can think again smartly in 10 seconds, but I don't recommend that idea of thinking, because in some problems you will be stuck. And so you should think in terms of energy. Like I will give you a very simple problem. This is a very conceptual Olympiad problem. If I can just take your time here. The problem is something like this, that there are two guys, like these are two hills, like, and I've got a object which is in the form of a right angle L-shaped body, and at the bottom there is a point object. If I can just explain that to you, I don't have that. Like, ऐसा कुछ है कि एक L-shaped body है, और these are like light rigid rods, and there is a ball here. So what I will do, I will quickly read that problem for you, just so that you can make some build. The question was like this. This is a light thin rod bent into a right angle, and there is a massive bead here. There's a massive bead here, right? Structure ko humne rakha. These are frictionless platforms, so there is no friction here. No friction here. And remember, here also we don't have any friction, so no friction. We are in a vertical plane, so gravity is present. Everything is fine. The question is, when the structure is in equilibrium, this structure is in equilibrium, these are long rods. What is the distance of this massive bead from here and from here? So I can give you objective question. This distance is greater than this. So like x1, x2, I've given you, this is 90. So I can give you objective x1 greater than x2, b x2 greater than x1, c x1 is equal to x2, and d we can't determine. Maybe if I just write that. Remember what I am giving you again. I am not providing you any information regarding the height of this guy. There are two hills, like frictionless vertical bodies, and they're fixed. Between them, I take a rigid structure which is bent in the form of a right angle, and I have a massive bead which is welded here. And when I put this system between those 2 points, it takes an equilibrium position, which is shown in the diagram. When it takes the equilibrium position, I ask the question, what are the distances from here to here? And I gave some options. So I'll give you some time, all of you, to think and solve your way. And the reason I'm taking this question is, again, be very clear. Like, I mean, I don't want to solve this problem like this. Somebody will say mg will act, normal reaction will act, normal reaction will act. I will balance the torque. I will balance the forces, n cos, then some divide, then some theta, and then some relation. You will get an answer, but that's not a beautiful way of solving this good problem. Can somebody, like, method 1 is fine. First of all of us need to understand that method 1 must be known, then only you can appreciate the second method, which I want to tell. Otherwise, we will be stuck. Question is solve me, or what's the point in discussing method 2? So let me just go through that method 1 and explain this small basic problem. Somebody can say mg will act here, sir. There will be a normal reaction. So let me write n1. This is 90. There will be a normal reaction here. Let me write n2, 90. By absolute basics, student will say, sir, I will form this triangle. And this is 90, this is 90. And what I should say, let him take some angles here. So if you take this angle as alpha, and this is 90 minus alpha, this angle here is then alpha, 90 minus alpha. This is again 90 minus alpha. All those things are happening. And then I can say that fine, like this is 90 minus alpha, so this is alpha. And similarly here, 90 minus alpha, so this is 90 minus alpha. So like this is one method, n1 sine alpha is equal to n2 cos alpha. And then if this length is L1, this length is L2, second equation is n1 L1 is equal to n2 L2. So somebody will write like tan alpha, sin alpha upon cos alpha, n2 upon n1 is L1 upon L2. And when he says L1 upon L2 is equal to tan alpha, then he gets the relation that x1 is equal to x2. Because x1 can be written as L1 cos and x2 can be written as L2 sin. So student can say, fine, sir, I got that. L1 cos is equal to L2 sin. So my x1 is equal to x2, and they are incorrect. This is answer. So that is what I'm saying. These are conventional approaches. You should not be. Now think beautifully. This is a concept of stable equilibrium of this point object. Whenever you keep this body between two hills. This guy will keep on moving on a circle because like this angle is 90. So they will always form a circle, and this is the angle in a semicircle. And out of all the possible circles, our guy will always take a position which is the least potential energy position. So it will go to the bottommost point, the point where tangent is horizontal. And then when it attains that bottommost position, that is only possible if x1 is equal to x2. So I did not do all these things. I'll directly say by energy, you give me a structure, you leave the structure. So by slippery motion, the structure will try to orient itself in such a way that it attains a minimum potential energy. Now, when it attains the minimum potential energy, definitely that angle is 90. So a circle will be formed between those 3 points. And the hill points will be acting like diameter. And we are at the bottommost point of that circle because of least potential energy. And if I draw a tangent there, that is a horizontal line. That is only possible. And center is exactly at the middle. So when the center will be exactly at the middle, the distance this and this is equal. So this equal. So x1, x2 equal, we are done. The C option is correct. So just I got digressed because I thought we should be thinking on those lines as you are nearing your exam. So please think more while solving the examination paper of physics. And if I can just quickly go through one case, so many problems. I'll take up problems in the next class, maybe, which I can take up. Let me take a very simple question. Just solve this for the heck of it. Like, just read it and write the answer directly. 2 minutes. Thin disk, radius r, held closing the opening of a thin hemispherical shell. So hemispherical shell, और उस पर डिस्क लगा दिया, उसको पकड़ के रखा. No gravity. Both the bodies are made up of insulating materials and have uniform, so they are insulators, and they have sigma. And now the plate is released, keeping the shell fixed. Shell is fixed, and I release the plate. So now it starts moving. It goes up to, the question is, what is the maximum kinetic energy acquired? Still a nice problem for advanced. Just think and tell me, how will you calculate in a, like, read the question and immediately write the answer. What can be that approach? One line. Because it is insulating. Now you understand, we cannot solve like this ki ek hemisphere rakha hai and there is a disk here. Hemisphere is charged, disk is charged, so they will have repulsions. So repulsion will let it move. All those things we understand. So finally it will go up to infinity because of those repulsions. So question was direct. What is that energy? So I will write in a line. My answer is whatever is the interaction energy at this stage. And interaction energy at this stage, how to write that? So I'm saying because of, now something I'm writing, you just think why I'm doing this. I will directly take his charge. I will say sigma pi r square, right, into k by r, k is 1 upon 4 pi epsilon naught, into sigma into 2 pi r square, and I'm done. I think you understand that I'm right. I'm writing. The good thing is, because of this hemisphere, the potential at all the points were constant. So I just wrote potential at the center, and potential at center is just potential at all the points. And why this statement is correct is because if you take a hollow hemisphere, you understand that field at all these points will be normal to this disk. And if field is normal everywhere, whatever be the magnitude, potential is constant everywhere. So just write potential at the center and multiply with the charge that you have kept on the disk, and you are done. And why field is normal everywhere, you understand by principle of superposition. If this is hemisphere, and if the field was not normal, it would be something like this. If this is something like this, if I cover the lower hemisphere hypothetically, the other field will be this, and the resultant will be forward. But the resultant field inside the hemisphere is 0. So only possibility is, because of a hemisphere, at all the points here, the field should be normal. A field is normal, potential is constant. So potential at center is potential everywhere. So potential into charge is your interaction energy. You're done with the problem. Indirectly, you can think and answer these small questions. So there's no point integrating and taking combinations, not even required. Perfect, students. I have to rush for another class in CO Center. So see you in the next class and just go through these concepts which I've told. I've tried to cover fluid, mechanics, electro. Like I'm trying to combine as much as possible. Bye-bye. Take care.